All right. So we didn't get through all the stuff on lists before. We're going to cover more about lists today. That's fine. I usually don't make it through that lesson. There's a lot going on in that lesson. So today what I want to do is just have a recap, an overview, and talk about what we talked about last time regarding functions and lists. Actually, that's our recap. So first, I want to go through this overview again. For some of you, this might feel a little redundant, but I want to be really clear about like how everything we're covering fits together, like where it fits and like what we're heading to in Premium Prep, what the intended material to cover is, right? So the idea again with Premium Prep is that we want to give you a complete but very basic set of tools to start to be able to program, right? So in order to have a full but minimal command over a language, that's going to involve understanding the data types, how to write abstractions, in this case functions, being able to write conditional logic, conditions. This is if, elif, else in Python, and being able to write loops. Today we're going to talk about loops. So that will all the type. Let's recap this a little bit. So the types that we've talked about are int, float. These are our numeric types. Bool is technically a numeric type, although I'm going to kind of stick it in its own category. String and none. So these are all the simple types that they're immutable, so that they don't have the capacity to change their value without changing just a different object, right? So yeah, all these have basically a fixed value and they're immutable, which means we can't change them once we set them. We talked about lists the other day, and this is our first mutable type that we've discussed so far. So these are the types that we've talked about. Some other types that we're going to talk about are tuple, and I'm going to put an asterisk next to the ones that we haven't talked about. Tuple. So tuples are very, very much like lists, except that they're immutable. That's really the big difference. And then we're also going to talk about dictionaries. This is basically the last really important type that we haven't talked about, and we'll get to that. And then sets as well. So there are only 3 types left. I feel like, gosh, I have this feeling like I'm missing something obvious, but yeah, okay. So there's only 3 types left that we are going to discuss that we haven't discussed yet. And of those 3, dictionaries are basically the major one. And these other 2, you'll see how they fit in. But yeah, cool. So these are our types. These are our basic built-in types in Python. We've talked a little about each of these. We're going to talk more about lists today. So functions allow us to encapsulate. Encapsulate, that was the word. When I was trying to write this last class, I was like, wait, there's a word that I always use to describe this. I couldn't remember encapsulate. So encapsulate, this allows us to encapsulate a process. So we can create a container for the process, write the process or write the algorithm once, and then utilize that algorithm wherever we want in our code without having to write the whole thing from scratch every time. It helps us keep our code organized, and there's some really cool things you can do with functions. although really the main selling point here is that it makes your job easier. You don't have to do work redundantly, and yeah, you just the way you think about your code doesn't have to be, yeah, it just helps you think about your code basically. Conditions are obviously pretty necessary. We don't want the program to do the same thing every time. We want it to do things dynamically based on factors, based on whatever other factors. So being able to check conditions will allow us to execute code under certain circumstances and not under other circumstances. So obviously that's pretty useful. Loops allow us to repeat a body of code. Loops / iteration. So just repeat something in our code. It'll allow us to do repetitive tasks, right? So we've talked about all these, you know, I noted the types that we haven't talked about yet. We've talked a little bit about functions and conditions, and today we're also going to talk about loops. So just for context, we're going to start off with lists. We're going to talk about loops, and then we're going to go back to talking about lists again. Lists and loops are often go together. So lists are a data type, and loops are just sort of another important construct here. Okay, so just to recap for functions, so I want you to create this really strong distinction with functions. So with functions, we'll use the word function to describe a function definition and a function call, right? You know, I might say len is a function, right? Or I might say right? I might define a factorial function and I might say, well, this is the factorial function. So we'll use the word function to describe both the invocation and the definition. And there's a bit of a conflation. Well, it conflates the two. Using that word, I've noticed like that conflates the two in a way that makes it sometimes hard to think about if you don't take the step of deliberately making a separation between this is an invocation of a function that's already defined somewhere, and this is a definition of a function that is not invoked, right? So any function that you're invoking has to be defined somewhere, and any function that you're defining somewhere has to be invoked, otherwise it's not going to run, right? So I'll give you an example. So if we do the factorial function, if I say prod, and I'm assuming you all know what, you know, just know what factorial does, really, but well, if you don't, a factorial, so the factorial of a given number is every number, you could say starting at 1 or 2, it actually doesn't matter. Every number from 1 or 2 times every other number sequentially up until and including that number, right? So factorial of 4, we can determine factorial of 4 by doing 1 times 2 times 3 times 4, or 2 times 3 times 4. So I'm going to say for I in range 1, or we'll do 2 to n plus 1, prod times equals I, return prod. Okay. So I'm using this factorial function. I know we haven't talked about for loops yet, but we're going to today. And what I'm doing here is I'm just starting a value at 1 here, and we're just going from every number in a range from I through range starting from 2 to n plus 1, right? So if n is 4, we're going to do 2, then 3, then 4. And we're going to multiply that value, 2, 3, and 4, which I'm calling I here. We're going to multiply that by whatever the current value of prod is, and then save that as the new value of prod. And then after all is said and done, we want the output of this function to be whatever the value of prod is, product. Okay, so if I were to ask you, if I were to say to you, if I ran this code, what would happen? Your answer should be nothing. Nothing will happen if I run this code. I mean, let's prove it. This will take a second to, I don't know why my interpreter is slow these days, but it'll take a second. And I mean, it'll take a second and you'll see nothing. Let's do that. Yeah. So the reason nothing happens, I wrote all this code and nothing happens because this is a definition of an algorithm. When you're defining a function, you're defining the form of an algorithm. That sort of, I worry that makes it sound harder than it might be, but basically all that means is that the values for the inputs aren't supplied yet. That's all. That's all that really means. And what that does is it allows us to supply those later. And that's all that's necessary for building something that is a general form rather than tailored to a specific task, right? So this is not tailored to, this function definition shouldn't be tailored to calculating the factorial of 4, right? Because then it doesn't, it doesn't matter, right? Like I should call this factorial of 4, right? And then every time maybe I want factorial of 5, well, I'd have to copy my whole function here and do factorial of 5. We don't want to do this. Hopefully it's clear that we don't want to do this. We don't want to rewrite the whole factorial function every time we want to do a factorial of a different number, right? So what we do is supply an argument or a parameter, more accurately a parameter, and we don't give it a value. So this is an important thing. During the definition, the inputs don't have values. If they had values, they would be, specifically baked in for that specific function, right? So what I don't want you to do is say n equals 4, right? This is not going to help you run your function with n equal to 4. Another thing I don't want you to do is n equals 4 here, because this does the same thing, right? When I call this function, whatever I passed in as n, if I pass in n as 5 here, well, it doesn't matter because I just overwrote n, which was 5, to 4. So this is now, again, I should call this factorial of 4, right? So how do I actually utilize this? Well, I have to make a call to the function. Now the function has an output and I want to see the output. So I want to print the function call to see the output, right? So when this function runs, it's going to return whatever the value of prod is. And in order that we can see it, I'm just going to print it out. And then I'm going to replace what's ever in the parentheses with the appropriate arguments. So if I want to do factorial 4, I invoke the function. It says factorial and it sees 4. So it goes back to the factorial definition and plugs in 4 for the value of n. And then anywhere where you see n, you can just replace, you can imagine 4 in its place, which is right here, right? So we can imagine 4 in that place. And then if I want to do factorial 5, factorial 37, whatever. So this will allow me to do factorial of any number. So there's a few, I want to be clear about this. There's a few pitfalls that I want you to remember to avoid, right? We don't want to set the value to test here or the value to utilize here. We don't want to set it here. We want to use it here. Now, if I wanted to do something like this, num equals 4, this is fine. because I'm still, this is a global variable, but the way it finds its way into the function is what I like to think of as through the front door, right? You can think about this is the way I thought about it, and I'm not sure if this is going to be necessarily useful to you all, but when I was learning this, the epiphany that I had and the analogy that I came up with is like, this is like the front door, right? This is the customer entrance, as it were. So this is, if you have a global variable, it can go into your function, but the only legitimate way that it should go in is as an argument in the parentheses into the function. That's fine. That's totally fine. It should not do this, num, right? We should never do this. And if we can set local variables in the function. If we have something that's global, right? Right. If we have something that's global, the local version will override it. So we can set local things, and that's totally fine. But you don't want to, I wouldn't want to like just take in and then set in here right away, because then there's no point in taking it in. I might as well just leave it empty and then just plug in a value here, which kind of defeats the purpose of a function in most cases. Okay, cool. So that's our function. I'll just call that good on our function recap. Oops, let's do this, num equals 4. Then what we talked about regarding lists last time, we talked about lists being mutable, ordered collections of arbitrary objects, right? So mutable means that we can change, we have different tools that are built into part of the list class that allow us to add things and remove things and move things around. There are various ways of altering the values of a list. So that's what mutable means. Ordered means the order that we arrange things in, or the order that we add things into the list is preserved. It's important and it's preserved. And you might think, well, yeah, I mean, of course, why wouldn't it be? This is an engineered thing. This is a feature that is engineered to be what it is. This is not a given, and there are other types that don't obey an order in the same way, or that we think of as unordered. I think Python at this point has standardized everything so that everything has a predictable order, but I think, like, for example, I think sets are just sorted. So if you have a set of strings, they're going to be sorted alphabetically or lexicographically alphabetically. I believe that's the case. So they will not reflect the order that you add them into the set, for example, right? So it's important, we don't have anything to juxtapose this against yet, but it's important to establish this idea now. That way it's not weird when we encounter types that don't obey an order. Okay, so mutable means that they can change. Ordered means that their order is preserved. Whatever order we give it, however we arrange things, is going to stay that way until we arrange them differently. They're a collection, meaning that they're a group of other objects being any of the types. Arbitrary collection of arbitrary objects means we can mix and match objects. So the reason I include this, if you're coming from C or Java or something, you may be familiar with arrays that, like an array of integers that are an int array can only hold other it can only contain integers, or a float array can only contain floats, or a char array can only contain characters, or things like that. Python lists are capable of containing any mix and match variety of types. So I could have a string and an integer and a float and a bool and another list and another list, whatever. So there is no restriction, and to my knowledge, there's no way to apply a restriction to the list type in terms of what data it can contain. Okay, so this is what a list is. We covered indexing and we covered ranges. So a range again is not a list, but it's, when we get into loops, we'll see that they have a somewhat of a role that can overlap with each other. So we talk about them with lists because they kind of go hand in hand a little bit. And the object that range returns, so range actually returns, range technically is its own type. It's not a list, it's not any of the other types, it is the type that range returns is a range. But we don't consider it one of the types, because one of the types up here, because it doesn't have a literal form. It just has, yeah, well, suffice it to say, for now, we don't consider it one of the types in the same way. It's sort of its own purpose-built little thing. So range just generates a range of numbers. The range function takes 1, 2, or 3 arguments in any case. The only acceptable arguments are integers that define the boundaries and the step. So if you supply 1 integer as an argument, that integer will be used as the upper bound. The range will start at 0 and go up to, but not include the upper boundary. So range 10 will be, or let's do range 5. If I did range 5 will give me numbers between 0, 1, 2, 3, and 4. But 0, 1, 2, 3, 4, 0, 1, 2, 3, 4 is 5 numbers. And that might seem trivial, but that's important. If I give it 2 arguments, the first argument will be the lower bound. So range 3, 5 is going to be, give me numbers 3, 4, and 3 and 4. If I give it 3 arguments, let me do this. If I give it 3 arguments, we'll do 3 to 10 in steps of 3. The third argument is going to be step, so it's going to be the start, the number to start on, the number to go up to but not include, the upper bound or the stop, and then the step, which is 3. So we'll go 3, 6, 9. That's what this range is going to give me. Okay. Cool. So let's recap indexing. And this is really going to be the start of our actual lesson today, because we're going to talk about slicing. That's where we left off last time. We're going to talk about slicing, and slicing is very much related to indexing. So let's review indexing again. So indexing, there's this idea that lists contain elements. These are all integers in this case, but regardless of whatever the types are that the list contains, we just referred to them in a generic sense as elements. So these are the elements of the list. They all happen to be integers. So 9, 8, 5, 7, etc. So each of these elements has a numbered location, right? So this this 7 is at location 0, 1, 2, 3. So this is at location 3. Now it might look kind of weird because it's the 4th element, but it's located at the 3rd index. Okay, so the reason for that is the first element in the list is located at index 0. Its location is 0. So its index is 0, right? Yeah, so let's do this. So the way we access an index is I can say print list. Print's just going to make it so that I can see it, right? Print is not going to make the difference of whether this location is accessed correctly or not. It's just going to make sure that I can see it on the terminal. So we're going to print it out, and then I'm going to name. I'm going to supply the name of the list that I'm trying to access an index from, right? And if I want to do, let's say I want the 7, 0, 1, 2, 3. So that's list sub 3. List sub 3. That's the way we say this. So sometimes we'll say we're subscripting into index 3. And for short, I'll just say list sub 3. Okay, we'll run that and we should see 7 printed out. So if I supply a positive number, it'll go through and find the index at that number. But let's see. So this is index 3, 4, 5, 6, 7, 8, 9, 10. So I can go up to index 10. What happens if I go to index 11? That's going to be a index error. So this is its own error. If I ask for a number at an index that doesn't exist, I'm going to get an index out of range error. Okay. Here's a weird thing you can do. It's not, well, might seem weird now, but it's something that you'll actually use. So you can actually supply a negative number. You can use a negative number, and what that's going to do is it's going to count from the right hand side to the left hand side, and there's times where you really need to do this. So if I supply positive numbers starting at 0 or higher, I'm going to get a number from left to right, right? Counting from left to right. If I, for whatever reason, want to start from right to left, and sometimes you do, I can use a negative number. Now, -1 is the last or the rightmost element. So these two access the same actual element, right? So list sub 10 and list sub -1, right? Oops, I forgot to do that. The difference here is, I'm going to put this in here, right? The difference here is if the list changes in size or something, if I add something, list sub -1 is still going to find the last element, whereas list sub 10 is just going to find the 10th element, right? So what if I removed some things here, right? So list sub -1 is going to get me the last element, and then list sub 10 is going to be an index out of range, right? So using negative numbers can be really handy to save yourself the trouble. I don't just have access to -1, -2, -3. It's just starting from the right-hand side where the rightmost number is -1, then from the right, -2, -3, -4, etc. So -3 will be 1, 2, 3. That'll be that 6 right there. Okay, cool. So that's indexing. Suppose it's worth mentioning that if we can get an index out of range error in the opposite direction. So I think this is gonna work now, actually. Yes, that's gonna work. Okay, so list sub 12 is now gonna give me an index error. And if I do list sub negative 12, is that gonna give me an index error? No, because that's gonna give me the first element, right? So list sub negative 13 is gonna give me an index error, again, index out of range. Right, so you have to be sure that the index you're using is within the range of the list. Cool. On to slicing. So slicing is similar to indexing. We use this, and I'm gonna just grab my list here. Oops. We use similar looking syntax. We'll say list, and I always say sub like this. I always say sub, and then the way I say this is list sub. Let's do 3 : something like this. So this is actually a slice. This is what we call a slice. And what this is going to do is give us a section of this list. So this evaluates to a portion of this list only. So if I do this, what it's going to do is it's going to start at index 3 and it's going to go to the end. So remember when we talked about start, stop, step with range? Ranges, arguments. If I did range 3, 10, 3, we want to start at 3, we want to go up to, but not including 10, and we want to stop, or we want to do steps of 3. So slicing has the same pattern, right? When we want to slice, we're just going to put in 2 colons like this. Now, quick caveat here, this is what I always do. I always put in 2 colons, and while you're learning, I think it's easier to learn this way. I think it just kind of keeps it clearer. You will see this done with 1 colon. If you want to only supply a start and or a stop, you can use 1 colon like this. I always use 2, just, I don't know. It's just a stylistic preference that I have. And I think it makes it, like I said, I think while you're learning, I think it makes it a little clearer because you always have start, stop, step, sort of object or more clearly delineated from each other. So, okay, so the starting index will be index 3, so that'll be that 7. If I don't supply something for the stop index, it's just going to go all the way to the end of the list. Pretty easy. If I don't supply something for the step, it's going to assume that I want steps of +1. +1 will take me, it'll start at 9 and then 8 and then 5. I don't have to supply something for the start. I can just supply something. Maybe I want to start it at the beginning and go to index. I want to go to index 3 here. So remember, just like range, the stop, excuse me. Gosh, I get hiccups all the time in class these days. The stopping point is not included, right? So it goes up to, but does not include the stop. So index 0, 1, 2, 3, 4. So I want to go up to index 4, but not include it. If I don't supply something for the start, which is totally fine, you don't have to do that. It'll assume that you wanted to start at index 0 or at the beginning. Cool. So this is going to give me this, which is beginning to index 4. I'm just going to say excluded. And then this is going to be, let's do this, index 3, or let's do index 7. How about that? So that'll give me this, which starts at IDX 7 through end of list. And then we have a step. So I could take steps of, why don't I take steps of 4? 9, 3, 3. So that's going to be 9, and then 1, 2, 3, 4. So that'll be this one, and then 1, 2, 3, 4, and then that'll be that one. And then we can't count another 4 before the list ends, right? So oops. Fine. 9, 3, 3. Start at the beginning in steps of 4. Okay, so I got a challenge for you. What happens if I do this, -1? Step of -1. What's this going to give me? Any ideas? Go ahead and put it in Slack if you've got an impression about what that might be. And it is valid code. It's a bit of a curveball, but I can't get anything over on y'all. I think I'm like, I got this. This'll stump them. All right, yeah, so this reverses the order of the list. So there are times when you want a representation of your list in reverse order. So list sub : -1. That'll give you a reverse of your list. Well, I say reverses, it really, reverse version of your list. It really gives you a reverse version. Cool. Okay, so that's slicing. Quick note on slicing. Yeah, let's do this. Okay, maybe this will get you all. Okay, so remember what our maximum index was. Let's say I want to go to, I want to start at the beginning and go up to index 20. So anybody know what this is going to give me? Cool. So, yeah, so we've got a variety of answers for this one. So I'm seeing some people say that this is going to be an error, and this is reasonable to think because if we were indexing, this would be an error. There are not 20 elements. There is not an index 20 here. So we can't index with we can't index into the location 20. We can slice and use something that is beyond the bounds of the list, though. And it's kind of a weird one. So in this case, this is just going to go as far as it can, and then it's just going to stop when it can't give us any more. So this is fine. This actually works fine. You know, I could start at index negative 1000 and go up to index 20, right? So it's fine. You can use an index that's out of range while you're slicing, but not while you're indexing. It's kind of a weird one. This can be useful, like, you know, if you want to set a limit to something, you have a list of an unknown size, and you're just like, well, you know, I don't want to get more than the first, you know, 100 elements, you know, and if there's less than 100 elements, well, I'll take those. But if there's more than 100 elements, maybe you just want the first 100, right? You want to limit its size in some way. So this kind of thing can be useful, and I'd say 100 here, or 100 like that. Okay, cool. Nested lists. This is something that comes up occasionally. I don't want to spend a whole long time on it. Remember when I said lists are collections of arbitrary objects? They can hold any other data type, including other lists, right? So so here's a question. How many elements are in my variable list? Cool. So this variable contains 2 elements, which are just happen to be 2 lists, right? So remember, I can subscript. So how many elements are in list sub 0? Yeah. Yep. So we got 3 elements in list sub 0 because list sub 0 gives me back this list. So this list sub 0 refers to this list. How would I access this 9? How would I print this thing here out? How would I print this out? How would I access that and print it out? We'll treat this as kind of a breakout. Go ahead and put in your answer. And do please, if you're submitting code, do please include the triple backticks. Do that, and it'll format it like code, and it'll look a little cleaner. So no worries if you didn't do that. I'm, you know, like trying to get everybody in the habit of that slowly. So, you know, it's all good. Cool. Yeah. Yeah, so that's going to be list sub 0 sub 2. So this looks kind of funny, but I mean, we can, you know, as many nested lists as we have, we can just keep adding in, we can just keep subbing into those successively. List sub 0 sub 2, sub 4, sub 9, whatever, you know. So if we had that many nested lists, which thank goodness we don't. But this is a string. So here's a side note. Everything we're learning about indexing and slicing for lists also applies to strings, right? So actually I could, if I wanted, okay, let's say I want to print out thing from here. How would I do that? I'll up the ante on this one. So how do I print out thing? Given that, and you know, we haven't discussed this explicitly in terms of strings yet, but given that I'm saying everything we're learning about slicing and indexing also applies to strings, right? So list sub 0 sub 2 is a string. Therefore, it's sliceable and indexable. When you index into a string, you just get a character. When you slice a string, you get a section of characters. Great. I'm seeing a bunch of great answers. So we can do 5 to 10. So we'll start at index 5 and go up to, but not include index 10, and that'll print out the word thing, right? And that's because strings are 0-based indexed, right? So T is index 0, H is index 1, 2, 3, 4, so 5. So we want to start at 5, 6, 7, 8, 9. We want to include 9, so we want to go one more than 9, which is 10. So we'll go to index 10. Now, yeah, there we go. That's nested lists plus something else. There is a breakout in there. You can do it for part of your homework if you want, but we had a couple good sort of improvised breakouts that I think are fine for this. And I want to get on to mutability. Okay, so we're going to explore this idea of mutability more. So in order to talk about mutability, the way we can tell in Python, the way we can tell if a type is mutable is if it has mutable methods. Essentially, that's how we can tell. So if I say list equals, yeah, let's just start with an empty list. There's a method built in for lists called append. And append, like the name suggests, will append a value onto a list. So I'll say list dot append hello. And if I want to append something else, I'll say list dot append world. And I'll print list. And why don't I print list at every stage here? So I'll print it after I create it when it's empty. Then I'll print it when I add hello, and then I'll print it when I add world. So this is what's meant by mutability. And I want you to draw a distinction between this and things like list or string concatenation. Remember when we had string concatenation? We talked about string concatenation. So if I do string equals let's do this. String 1 equals hello, and string 2 equals world. String 1 plus string 2, print string 1, string 2, right? So me adding these together doesn't alter one of the strings. The strings still stay the same. And I mean, this might be obvious. Hopefully it's clear, but this is because strings are immutable, right? There's no operation in Python that will change the value of the string other than to just say, if I wanted string 1 to include world, I would have to change it by reassigning the variable. So string, if this was string 3, you could do that, right? But if I wanted to change the variable string 1, I would just literally have to reassign it. So this is not a mutation in the same sense. This is a concatenation and a reassignment of the variable. So this is different than the idea of a mutation. And we can kind of prove this. So there's another function that I want to talk about, which is the ID function. So let's do this. So ID, so what ID does is it takes in an object and it returns the ID given to it by the system. I'm not sure if the Python interpreter gives it the ID or the system gives it the ID, but at any rate, it gives it it returns the ID as an integer that object has, right? So if I have my object equals hello, right? And now in order to see the ID, we have to print it, right? We'll print the ID of my object. Oops. So this is the ID of that object here. If I run this every time, it's actually going to change. But for any given time running it, it's going to give me back the same number, right? For that attempt at running it, right? So as long as the program is running, it has that ID in memory. Okay, so this is how we can prove that something's mutable. So if I print, I'm going to print the ID of the list. And remember, ID gives back an integer, ID. Okay, so if I print the ID of the list, notice that they're all the same. I'm not going to read out this whole number, but if you want, you can look at the right-hand side, the last 3 or 4 numbers. If those don't differ, it's probably going to be the same number. Right, so the ID of the empty list is this. We append hello to it, and the ID did not change, which tells us it's the same list. We just changed the value, right? So if strings were mutable like lists are, we should see the same behavior if I did, let's do this. I'll make a variation of this. Let me my string equals empty string, and then I'll print the ID of my string. And then if I say my string equals my string plus hello, and then I'll print the ID of my string, and then my string equals my string plus world, and then I'll print the ID of my string, right? So hopefully this is kind of clear, right? I'm trying to do something similar in either case, right? With list.append, I add something into the list. And when I use this list variable, it now has a different value, but it has the same ID because it's the same list. When I do something similar, and we'll see it's not the same kind of operation, but it's just similar. There's hopefully an obvious similarity. In either case, we start with something that's empty and then we add some things to it, right? So the first thing I add is I say it's equal to the value of my string, which is an empty string plus hello. And then it's equal to the value of my string, which is hello plus world. I don't need that space there. And after each time I change the string, I'm going to print the ID. Oops. This is confusing. Okay, so notice, so this is the first ID. This is the second ID. And this is the third ID. And that's because each of these concatenations evaluates to a literally different string, not just different in value, but a different string in memory. You've now made a new string and you've put that new string in your memory. The old string is still around. Since we're reassigning the pointer, the identifier, which is the name portion of the variable, since we're reassigning it, and we can tell we're reassigning it because of this equal sign, since we're reassigning that variable, the old string is now what we call orphaned. It no longer has a variable, or it no longer has an identifier pointing at it. So since it no longer has an identifier pointing at it, the Python interpreter is smart enough to do what's called garbage collection, which is it goes around and it finds orphaned parts of your memory, and it says, oh, well, there's no pointer pointing at this, so it's inaccessible, so I'll delete it from memory. The way it schedules that and deals with that is complicated, and you can't really count on it being consistent, especially across different different builds of the Python interpreter. So that's just something that happens in a black box behind the scenes. Just know that it will happen eventually, but there's some overhead for that potentially, right? There are different kinds of overhead in building a more complicated type that's capable of growing and changing and having its value mutated. So on the whole, as these two shake out, they can be very comparable in terms of performance. Using something that is immutable and changing it in this way can be comparable in performance to using something that's mutable. In certain circumstances, one may outperform the other. And in most circumstances, especially where Python is concerned, optimization, well, most like real life circumstances, optimization is just not really a concern. So yeah, I don't want to. I know people will look at these and try to think about like what's the, highest, the best case optimized way of doing things, and that's fine. I like the kind of thinking of like optimizing coding, but if you're new to programming, it's one of those things like you can overestimate the value of memory optimization. A lot of times it's just not important. It's just not a concern that you have when you're solving a problem. Sometimes it very much is though, but for this purposes of this class, optimization is basically never going to come up. Okay, cool. So since we can mutate a list and change its value without changing the list itself, that can get us into a situation where we lose or alter data that we didn't want to alter, right? So it can be really useful to make copies of lists. So if I do, I'll call it list 1 equals 4, 3, 5, and I want to list 1 dot append hello. So I make a change to my list and I print list 1. Come on. Oh, didn't run. Okay. So let's say I didn't want to alter this original list for whatever reason. I maybe I need to do the alteration, but I don't want to do it to this list. I want to keep this particular list intact and do the alteration to a different list, right? So I would want to copy list 1, right? So I'm going to show you the wrong way of copying, because it's this seems intuitive to just say, okay, well, let's make another list, call it list 2, and set it equal to list 1. Who knows what's going to happen here? If I append to list 2 instead, and I print list 2 and list 1, who knows what the value of list 1 is going to be? And list 2 for that matter. We could do list 2 too. Also, again, to reiterate, an acceptable way of answering this question is by running this code and seeing what it gives you. And if you don't understand why, then saying, hey, this is what I got. What's going on? We have somebody saying, well, I'll wait for a few more answers here. To somebody asking about deep copy, this is what I'm demonstrating is called a shallow copy. Okay, so yes, somebody says they have the same ID. They do have the same ID. So somebody's, the first comment in response here is it appends to both lists. You're correct that both, let me put it like this, both identifiers will have the same value. If I print list 2 and I print list 1, they'll have this, I'll get the same value. I will literally get the same value because here's the thing, there are not two lists. There's one list. I'm not trying to put you on the spot or anything. You're thinking about it correctly. You have a good understanding with that comment. But I do want to clarify, there aren't two lists. So let's just prove this. We'll look at the values and then we'll look at the IDs. Okay, so these are the values. It looks like two lists that have the same value, right? Let's print the IDs. Same ID, right? So what's happening here is this is one list that has two identifiers. And that's the thing that's possible. So the identifier list 1 and the identifier list 2 both literally point to the same list. So remember what I said at the beginning here. This is how not to copy something. And I'm showing this because it's a pitfall that will probably come up. And it's to be avoided. Oops. Okay, so this is sometimes called a shallow copy. It shouldn't be called a copy at all. It's just a, what would I call it? A pointer duplication or something, like where we have like, we just have a duplicate or a secondary a pointer identifier, I mean. You know, so this kind of assignment, and this tells us something about how Python works, right? When we use an equal sign like this, it says point this identifier at this data, right? So I make the data in here, and then this says point this identifier at this data. This data evaluates to this data, so it just points at the same object in list, in memory twice, right? So how do we do this correctly? Well, there's a few ways. The way that I'm going to recommend is to use the .copy, C-O-P-Y method. So copy, so now if I do this, so I append to list 2, so this is what's called a deep copy, right? And maybe we shouldn't call it a deep copy, but it's called a deep copy. I would call it just a copy because it actually copies, whereas a shallow copy isn't a copy at all. But those terms do exist and refer to each of those respectively. Okay, so now I say list 2 equals list 1 dot copy, then I append to list 2, and you can see I print out the IDs of both, and they're going to be different IDs. So let's look at the values too. So list 2 will have the value appended onto it, but my original list, list 1, remains untouched. So I want to be clear here, because I've seen a lot of people, when I go over copy, I've seen a lot of people like start like doing copy on everything, because they're like, oh, well, you know, I might as well make a copy and then do it on, make a copy of this string and then alter the copy of the string. So the .copy method does not exist for any immutable type, any non-mutable type, because, you know, like altering a string is kind of copies it anyways, right? Like this concatenation gives back what you might call a copy, an altered copy of the string. So you could think about strings being self-copying if you wanted to, or you could think about immutable types being self-copying. So the only way you're going to lose access to the original data is if you override the identifier that is holding that data. Kind of got to go a little out of your way to do that, and there's times when you want to do that, but it's very much in your control. So even though mutable types are powerful, immutable types have sort of an advantage of being less powerful, and that gives them the ability to be sort of more predictable, more controllable. There's sort of a safety there that's kind of nice. But both are necessary, obviously, for a complete picture of data types and programming. Okay. Quick side note here. I want to spend no time on this, but it's mentioned and it's worth mentioning. Oh, these quotes. Okay. I think I don't know how to spell fruits. I apologize. Oh wait, it's right there. Fruit. Okay. Why does that look wrong? I don't know. Apologies. This is where my dyslexia is in full overdrive. Okay. Okay, let's do this. So fruit list is grapes, blueberries, and apples. Then fruit 1, fruit 2, and fruit 3 equals fruit list. So this is called unpacking. So fruit 2 is going to be, anybody want to guess? See if you can guess before my weirdly slow interpreter takes its time to execute. So there we go. We got blueberries. So fruit 2 is going to be blueberries. So this works if you know the size of the list, but if you do something like fruitless dot append bananas, anybody guess what's going to happen? Value error, too many values to unpack. So it expected 3 because I said fruit 1, fruit 2, and fruit 3, but there were 4 elements in the list. So what's Python supposed to do? And if you have an assumption about what it should do, I could probably think of another 3 that would be just as reasonable. So there isn't an obvious thing to do, and when there isn't an obvious thing to do, Python will generally throw an error, which in my opinion is really the right behavior. Okay, cool. So I don't find myself using unpacking on lists all that often, kind of for this reason, because since lists are mutable, I can't really make guarantees about how many elements are going to be in the list. So maybe you do some type checking, or you check the length ahead of time. You make sure, if len list equals 3, then you can do your unpack. But that kind of stuff can get weird with like, what do you do if it doesn't equal 3? If it doesn't give you your length, do you have a different line of unpacking code for every possible infinity length of lists? I don't know. Sometimes it's obvious depending on the problem that you're trying to do, but not in this case, and not in a lot of cases. Okay. So unpacking is something that you can do. Not sure how much I use it with lists. Cool. Loops. I think we're going to need to get through this other stuff on Monday, alas. Okay, so let's shift gears into loops. So with loops, we're going to talk about, this is actually going to give us a complete overview of all the things at this point, right? So remember up here, we will have talked about a little bit of all of the major types. We know how to write functions, the right conditions, and we're going to learn how to write loops. So after today, you're going to have a complete, simple, but complete view of Python. You're going to, have a complete tool set, not comprehensive, but you'll be able to do stuff. Okay, so loops. We're going to talk about traversing a list. We're going to talk about accumulators, Boolean flags, list accumulation, loops as filters, break, continue, and pass. I want to mention this about pass actually right here. You've seen me do this a few times. Def, factorial, pass, right? So, if I'm just talking about defining a function really quickly, and I don't want to go like write all the whole rest of the thing, pass, when you see pass, you can think of it as a placeholder, right? So you might think, well, why do you need a placeholder? Why not just leave it off? Notice, I don't know if you noticed that, but my syntax highlighting changes on this line if I leave off the pass. If I leave off the pass, I'm going to get an indentation error. Or I might expect, unexpected EOF, since this is the last bit of code. Print. So if I do this, if this is no longer the last bit of code, I'll get I think this will be an indentation error. Yep, so it expected an indented block. So for parts of code that expect an indented part of your code, functions, conditions, loops, it's not that you can pass, it's not that you can provide something indented, it's that you have to. If you don't have anything to put there for now, and you just want to put a placeholder in, you use pass. And you'll see this all over our all over the Learn materials. I'm sure you all have already seen this a number of times in Learn. So pass's job is that it is valid code. It's code that Python recognizes, and pass, being valid code, does nothing. It literally performs no task or anything whatsoever. It's just explicitly telling Python, yes, I know there's nothing in here, and that's fine. And it'll be the Python interpreter will say, oh, okay, well, I'll just ignore it and move on then. So it's valid code that does nothing. Its purpose is as a placeholder. So it's just like saying pass, don't worry about it. And I'm just mentioning this now because we're going to talk about break and continue. Break and continue bear on loops. They're valid code that do something specific in the context of loops. Pass is always taught in every programming pedagogy I've ever encountered as a learner and as an educator. Break, continue, and passes are always taught together, and I think it's often confusing because break and continue have very specific roles in loops, and loops only. Pass has nothing to do with break and continue. So I don't know why they're always taught together, but I just wanted to mention this now. Pass is a placeholder. If you're seeing it in the code, that's what it does. I'll just run this and we'll see print hi, and that'll be clear. Okay. Okay, so the first type of loop that I'm going to teach you is the for loop. So for loops, there are two types of loops that we're going to cover in Premium Prep, which is for and while. So for loops are useful. So in either case, loops repeat processes. They allow us to iterate and repeat parts of our code. So in either case, they do that, right? So for loops are pretty easy to manage. You generally don't have to worry about them. They're easy to read and write. Once you know the syntax, how they work, they're pretty easy to deal with. While loops are a little bit prone to getting into infinite loops. There's a little more you have to think about, and there's more you have to manage. However, any problem that you can solve with a for loop, you can solve with a while loop, but not in reverse. Some problems you require a while loop to solve. Some of you may know there's so I'm being a little bit I'm euphemizing this a little bit. Technically there are ways of bending a for loop into doing anything you want it to do, but at some point it's kind of like you're pushing a boulder up a hill, and it's like almost more complicated than using a while loop at some point. So for all intents and purposes, for loops are a little less powerful than while loops, and while loops still have their role in certain circumstances. So fortunately, in my experience, and I think the other members of my team would speak to this as well, most problems that we encounter, we can use a for loop for. And the way we can tell, we can use a for loop for any problem that for any problem where the number of iterations is known before looping starts. So we can use a for loop where for any problem where the number of iterations is known or can be determined. Sometimes it's not known, but there's something quick you can do to determine the number of iterations needed to solve the problem before the loop starts. Now this sounds like, oh well, I remember like when I discovered this, it was like I was like, okay, well, you could. This will be a small set of problems, right? Because it may be really hard to determine a lot of times how many times you need to iterate through to something to solve a problem. And surprisingly, it's generally not. It's generally really easy to determine this, mostly because we tend to have like a known number of items in the form of a list quite often that we want to iterate through the list and go examine each item. And when we have a list, well, by default, a list does not have, well, let me clarify that. A list does not have an infinite size. Any list has a given size that we know when we start iterating through that list, right? A list has a finite size, so we can iterate through and we can examine every element individually in that list. And a for loop lends itself really well to that because a whole lot of problems are like fit that form. You have a list of events, a list of numbers, a list of words, a list of whatever, and you want to examine each of those. Maybe you want to check some conditions on each of those or run some process on each one of those elements, and you can use a for loop for that. For problems where you can't determine the end ahead of time for whatever reason, you have to use a while loop and loop until you find what you're looking for and then stop the loop. Okay, cool. So for loops. So let's have a list, and let's just say I'll just say 33 55, 44. So I'm going to say for num in list print num. And this is going to print out each number one over the other. Right now, this is the basic syntax of a for loop. We have the for keyword. We get to decide here the identifier name, the variable name, or the identifier for each of the elements in the list. Now, each of these are are numbers. So I figured num, num's a common shorthand for number. So I figured num is a good name since each of these are numbers, right? If I have a list with mixed data, I'm usually just lazy and I'm like, well, I'll just call this L for element, ELE, or ELEM are all shorthands that I use for element. I usually use ELE for element. So for element in list, print element. Right? Let's do this. I'll go back to it being a number for now, but I'm going to keep it, I'm going to call it element. So, so just to be clear, I get to call this part whatever I want. And then now I need a source for this identifier. I need a place where I can assign from to this identifier, right? So so for element in iterable, an iterable is some object in Python that Python considers iterable. Lists are iterable, strings are iterable. If you iterate through a string, you get the characters in the string. Lists are iterable, strings are iterable. There's ways of iterating through dictionaries and sets. And there are a number of functions that give us back an iterable as well. Range is iterable, and this is why we covered range, is because range, right? Range 10, right? So if I say for element in range 10, I'm going to get the numbers 0 through 9 printed out, right? So this is by far the most common application for the range function. You will see it outside of the context of for loops occasionally, but really you almost never see range not in the iterable portion of a for loop like this, right? This is overwhelmingly where we use range. And we teach it with lists because almost always when we have a list, at some point we're going to probably want to iterate through it and do something to each element in the list, right? So so this just prints out the element, but let's say I want to do something, right? So I want to square the element, right? So these are all numbers, so I can square them. Let's be clear here. So for num in list, actually, let's just, yeah, that's fine. For num in list, print num squared, right? So quite often what we'll want to do is we will want to accumulate the result of some operation that we do in the loop. Now this is called the accumulator pattern. I'm going to show you the integer accumulator pattern, or the numeric int float accumulator pattern. Let's call it the numeric accumulator pattern. What should I call this? I'm just going to call this ACC, which is short for accumulator. Accumulator equals 0. So when we start an accumulator, usually we'll start it at some kind of neutral value. It doesn't have to be a number. There are list accumulation and string accumulation patterns as well. But we're just going to look at a numeric accumulation. So we'll start it at 0. So we'll start it at something neutral or empty. Sometimes you'll start it at a different value, but in this case, we'll start it at 0. And maybe I want to ACC plus equals num squared. So this is actually going to be sum of squares. Sum of squares. And this will be the sum of the squares of the numbers from lists. So if I print sum of squares, we'll see that. And why don't I do something much more reasonable? Oops. Let's do, so this 3 squared is 9, 5 squared is 25, 4 squared is 16. So that'll give us something more relatable. So that's going to be 50. So 9 plus 25 plus 16 is 50. Cool. All right. So this is a basic sum accumulator. So let's look at a variation of this. So here we have a couple elements here that I can't square, right? So if I try, if I try to square the num, and now these aren't all nums, so probably better that I give this a different identifier, ELE, for element in list. Sum of squares plus equals element squared, but I can't square every element because some elements I just can't do that with. So I only want to do this if int, or if element is, if LA here is an int or a float. So I could say if LA equals int, or excuse me, oops, I messed up. If type, I have to do if type of LA equals int, or type LA equals float. So under this condition, these conditions will tell me whether I want to do plus equals here. Oops. Oh, forgot a comma. Missed a comma there. Okay. Cool. So we get a different result because we have a float in here too. 9.4. So there's a kind of a bit of a nicer way to do this, so we don't have to do two conditions. I can say if the type of element is in, and I'm actually going to use a tuple here. You could do a list like this, and I could just do a check for membership. So remember, we talked about checks for membership, right? This is one of the most common things that I do. I mean, actually, this specific line where I have a loop, I'm iterating through a list of mixed elements, and I want to pull out just the numbers for type or if type element in int and float. I mean, I write this line, this exact line here, a lot, or fairly often. And I apologize. Looks like looks like there was a question up here. Okay. Sorry, I guess I'll just save time for questions at the end. Okay. So sometimes when we're iterating through a list, we'll refer to that as traversing. You know, this is what we would call traversing a list. Traversing, like walking through, you know, we're walking through each element of this list. one to the next. I'm going to skip the breakouts. Apologies. Okay, accumulators. So I just showed you an integer accumulator. And this might seem like, okay, well, here's something that you can do. We're going to be looking at accumulators for other types. Like I said, there's other types of accumulators. If I wanted to do, let's just look at a similar version with a list. Let's call this squares list. I like to name the variable. I like to make the identifier name something that tells me what type it is. That reminds me of what type it is. So let's call this squares list, and I'll say dot append element squared, and this will give me a list of the squared elements, of the squared numbers. We got a little underflow here, a little bit of rounding error happening. Or excuse me, that's a rounding error, not underflow. Similar, but not the same. So this is a list accumulator pattern. So you can see like the pattern is very much the same as the integer, except we start with a list and we do a dot append. So at the moment of accumulation, that's a little different in this case. And that's generally where the differences in accumulation patterns are going to be. They're going to be at the creation of the accumulator and at the moment that you accumulate, or on the line that you do the accumulation. Sometimes for different types, there will be other differences, like dictionaries have this key and value thing where instead of indices, they have explicitly defined keys. So they're kind of like a list where instead of having a numbered index just automatically assigned, which they don't, they have an explicitly defined key. So there's some things you have to do. There's a little bit of juggling with managing what your keys are and what your values are for each of those keys. So that can change how the accumulator pattern looks a little bit for dictionaries. But other than that, generally that's like where the differences are. But we do think about the accumulator pattern being associated with each of the various types that we've talked about, maybe except for none, because I don't know, none only has one value. But there are string accumulators where we could accumulate characters or words into a string. There are list accumulators where obviously we could accumulate elements. Like I said, usually we'll start with something that is zero-ish or empty-ish, and we'll add things to it. That's what we can think about as kind of literal accumulation. Sometimes we'll start with something that has elements in it, and we want to add things, maybe insert them at different locations, or sometimes remove them. Like we want to filter through and remove them. Any problem that I've seen where that's framed in the context of like, start with this and do a decrementation or like a reverse accumulation pattern and remove all the elements. Any problem like that, you can always reframe it as a positive accumulation. You can always say like, well, I could remove the elements from this thing that has elements that I want to remove, or I could just start something empty and accumulate all the things that I want and just not add the things that I don't want, right? Like what if we called this num list, right? Num list. I could go through list and remove all the things that aren't numbers, or I could make another list and not add things that aren't numbers. So it's sort of 6 1, half a dozen or the other. The reason I'm mentioning this is because this pattern is so easy and it's so powerful. Like you can in a lot of cases, you don't even need to like reframe this and do some like negative or inverted or removal sort of pattern. There are cases where you I think the argument for doing that is really if you have it's really an argument of optimization. If you have an extremely large set of data and you want to filter it, you might not want to duplicate that data in memory. Like if it's like millions of records, um, that might be gigabytes of information. I don't know, potentially depending on what the information is. So you might not want to duplicate that information in memory arbitrarily. You might want to just like pare it down and reduce it down. But also, you might be able to get away with duplicating it in memory. Honestly, you might be able to. And also, problems like that don't often present themselves. You're not often up against issues like that. So it doesn't come up as much anyways. Not that it won't or not that it can't, but at least for now, in terms of beginner Python, this pattern of starting with something empty and emptying with something that's been populated by only the correct things, right? This line determines what's the correct thing to add, whether a thing is correct to add or not. And then this line adds it if it's correct. This pattern is simple and it gets a lot done. So I really, it's hard to overstate the importance of the accumulator pattern. It's something that you're going to do basically all the time. Sometimes it gets called the everything algorithm. And there may come a point in your coding where you're going to be coding a lot and you're going to realize, it feels like I just write functions with accumulator patterns in them all day, day in, day out. And that might sound boring, but it's actually kind of nice because it's like you have this, if you get good at the sort of patterns and sub patterns, if you get good at building accumulator patterns, like that's kind of it. Like that's a huge part of programming right there. Like you get a lot done just being good at the accumulator pattern. So I really can't, I feel like I can't overstate the importance of this. This isn't just another thing in passing. It's a very important one. Okay, cool. So accumulators are important. They can be thought of as a running total that held in a variable. That was sort of the integer example that I gave would do that. So the accumulator pattern is initialize the accumulator variable. What I'll often call this our target. And to be clear, we can have multiple targets, right? I could do both here, both the list and the sum thing, right? Right. So I could do this. So I would say usually you only have one, but there are times where you might have two or more. So you can do whatever you want. So you initialize your targets. And I call these targets because like those are the things that you're targeting. You start them as empty. They're not probably not useful until you've like done something to them. So, you're targeting these for altering, for changing, for accumulating onto. You repeat some process. Quite often you're going through a list or a range, or you just have some process that you need to repeat n times or whatever. And modify the accumulator accordingly, quite often under a certain condition. So you can see if this were wrapped up in a function, we'd be utilizing everything that we have learned thus far. And I'll give you an example. You've seen me write this a few times. This is why I write this. This is why this is the function when I need a small but complete function. Oh, it actually doesn't have any conditions in it, I guess, but still close enough. It's got everything but conditions. Right? So this has everything but condition checking. We've got our function. We've got our accumulator target. Since this is going to be multiplied against, I have to start it at 1, and that's why I say, that's why I'm avoiding saying like we always started at 0 or something. Like where you start your accumulator isn't baked in to be a certain thing, but in this case, since I'm multiplying against prod, I can't start it at 0, otherwise I'm going to multiply by 0 and then just get 0 forever. So I want to start it at 1, and then prod times equals I continually through this loop. So for those wondering why I'm calling this I, this is a convention. If you loop through a range, some range of numbers, it's convention to call this I. I've never actually heard in like a hard objective reason for that. Just that you can think of I as iterable, index, integer. So it just has enough. There are enough words that start with I that kind of give you the idea of a number in a sequence. Then that we'll generally call a number in a range I like this. So this is just a standing kind of long-standing convention that's been around for a while. So you'll see me do that. Okay. And yes, this is an accumulator pattern. So then when the loop finally terminates, the accumulator will have the correct value, or at least the value that you can process into the correct value. Like I mentioned, sometimes rather than starting with something empty-ish and ending up with something fullish, sometimes you'll start with something fullish and end up like reducing the size of it. Some people will call that a decrementation pattern. To me, it's always like initialize target, repeat some process for a certain amount of times, go through these elements in this collection, check a condition, alter target, and that pattern applies whether you're adding or subtracting or rearranging, whatever. So I use the term accumulator very broadly to refer to all of those kinds of patterns. Some people will juxtapose, like I said, the accumulation pattern against a decrementation or deaccumulation pattern or removal pattern, but it's all the same pattern. It just depends on what you're doing there, and most of the time you're adding. So I just call all of it accumulation. Okay. So sum accumulators using an int, we basically covered this. So for num in some collection of numbers, this nums could be a list of numbers, or it could be a range. Then we sum plus equals num. We can also calculate the sum of our list comprised of floats. Yes. Quick note here: if you have a list of numbers and you want the sum of it, list equals there's a function built in called sum. Takes a list as an argument. It takes a list of numbers as an argument and returns the sum of those numbers. So that's a nice, quick one, nice, easy one. Boolean flags. So Boolean flags are kind of what we think of as Boolean accumulators. It's just altering a Boolean value in a loop. You start something with false, you end it with true. Start something with true, you end it with false. You change it to false in the loop. That's all it is. At the end of the day, that's all it is. At some point, I'll go over Boolean latches. We're running a little light on time, but I'll go over Boolean latches, which is sort of a way of transferring information from one loop to the next or even successive other loops. It can be useful for that. So there are some tricky things that you can do with Boolean accumulators, and we will generally call them flags. So you set a flag to false and then you change it to true or something. So the isPrime function. Okay, so this is an isPrime function. This takes in a number and returns true or false based on whether that number is prime or not. This is using a Boolean flag to do that. This is actually not my preferred way of building this function. There's a better way to do it, and let's look at that. Okay, so isPrime takes in num. So one thing that I like to do is, before I really get into the definition, I actually like to write my tests first. Print. So I'm going to write a test, and we'll just say, let's just do this. 0, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So 0 and 1, whoops. 0 and 1 are not prime, so we expect this to return false. 2 and 3 are prime, so we expect this to return true. 4 is not prime, so that's false. 5 is true. 6 is false. 7 is true. So for those of you who don't know, a prime number is a number that has no other factors, no other whole number factors other than itself and 1. So everything divided by itself is 1. Everything divided by 1 is itself, right? So 1 and n are always factors of n, whether or not that number is prime or not. But a prime number is a number that has no other factors, no other numbers that divide evenly into it. So the way we can do this is we can say prime equals true, and I always like to just write in my returns right away. So return prime. So I know I'm going to return prime. And then I'm going to check an edge case here. I'm just going to handle numbers less than 2, and that'll become apparent why. So we'll say if num. Why is that written that way? Okay, sorry, this example code needs to be updated. This case is not the right case. So the correct case should be if num is less than 2, it's not a prime number. We'll return false. Oops, excuse me. I'm doing it the way that I like to do it. I have to remember prime equals false. I'm doing the Boolean accumulator way. Okay, so prime equals false instead of return. And then we can say for I in range 2 to num, there's a way to optimize this range. I don't want to get into the optimizations and complexities of that. So this will work, though, if you're wondering. So for I in range 2 to num, if num mod I, so that's meant to be mod. So if num over I has a remainder of 0, that's what this is saying. So if num mod I, modulo gives us the remainder of 0, then prime equals false. So it's not a prime number. And then once that's all said and done, we can return prime. So I have my tests here, 0 through 7, and I should see false, false, true, true, false, true, false, true. False, false, true, true, false, true, false, true. Cool, so that works. Maybe I should do this just to be clear. There we go. Okay, so like I said, this is, this is a Boolean accumulator. I know I know I've mentioned a couple times that generally optimization doesn't matter. There is a way to optimize this range so we don't check too many things, but generally I won't worry about optimization too much, except for loops. I will generally kind of try to make sure that I'm not doing too much excessive looping, right? So if at any point we find a value for I that is evenly divisible to n, we set prime equal to false, and then we go and check the next number to see if that's also, but we don't need to. We already know it's not a prime number, right? So for 9, for example, right? So I'm going to check every number between 2 and 8 to see if 9 is a prime number. Obviously, that's a little bit inefficient. But what this is going to do is it's going to check 9 divided by 2 is not equal to 0, or doesn't have a remainder of 0. 9 divided by 3 does have a remainder of 0. So we know prime, we set prime equal to false. And then this code is going to check the next number, which is if 9 over 4 has a remainder of 0, which it doesn't. But it's going to check all the other numbers, and we can avoid that by using the break keyword. Remember we talked about break. So break is just going to stop a loop. It's just going to stop this loop dead in its tracks. It's going to say no more loopage. So once your code encounters a break, and usually, I mean, you'll always put break under a condition in your loop, because if you don't, it's just going to stop the loop prematurely. So as soon as we determine that a number is not prime, we can just break, and that'll stop this loop from checking all the other numbers. And in this case, we'll just return right away. So my preferred solution for this is to use return, because return is also a de facto break. But it doesn't just break the loop, it sort of acts as a break for the entire function, right? So if num is less than 2, we can just return false. And then when your function encounters and executes a return line, it stops executing code. So it doesn't even go and do anything like checking the loop or doing any iterations and returning down here. It just straight up returns false and stops, right? Same thing here. We don't need to break. We can just return false. And that's a de facto break on the loop, right? Because even if we're in the middle of a loop, if we run that return, we don't do any more iterations. We just stop. We stop looping altogether. If our number is not less than 2, and we loop through the range, and we don't find a number that's evenly indivisible, a value of I that's evenly divisible into num, and we don't return false, then we've made it all the way through this loop, then we can just return true, right? So this is my preferred solution for isPrime. Cool. List accumulators we talked about. Using loops as filters. I gave an example of this just showing how to filter out the numbers from that. Just talked about break. This is an example of the Boolean flag one without that necessary condition. I know that needs to be fixed as well. I'll fix that using break, just what I just showed, and continue. Cool. So we are out of time. Suffice it to say, continue is like break for one iteration. It just skips to the next iteration. So that's something for you to think about. We'll cover continue in depth starting. We'll start here from for next class, but there's not too much to it, so you can probably figure it out on your own. Sorry for going over time a little bit. We do have just a ton of material to get through in the first few days, so it's just sort of a mad dash for me to get through as much as I can every time. But I promise we will get synced up. We will sync up, and we will get through all the material, and we'll start with continue on Monday. All right, let me stop the recording, and we can ask questions.